about Quillen metrics. So Quillen metrics have a now long history. They originated in, I think, Polyakov formulas for the determinant of Laplacian, Polyakov anomaly formulas, in the context of quantum field theory. And then there was a branching out to number theory, independent of Polyakov, which was the proof by Vortices of the modal conjecture, in which actually he was constructing axiomatically Quillen metrics. So I must say immediately what Quillen metric is. Quillen metric is a metric on a certain line, a complex line. And in that case, it will be the determinant of the cohomology. In the case of Vortices, it was the cohomology of a Riemann surface. So he was constructing certain metrics on the determinant of cohomology and showing axiomatically that they had some extraordinary properties. And at that point, Quillen came and realized that one could use Polyakov's construction of the determinant of Laplacian to give a direct analytic construction of the metric on the determinant of the cohomology. And ultimately, the theory of Quillen metrics branched out again towards number theory, towards more specifically Arakelov geometry, which in that context consists in extending, I would say, Riemann-Roch-Grothendieck theory, the theory of direct images, to vector bundles with metrics. That is, every time you have a certain data, algebraic data, you introduce some metric and you try to understand how does this metric behave under natural functorial operations. So let me, first of all, before giving the sketch of the course, say precisely what a Quillen metric is. So you give yourself X to be a complex Hermitian manifold. So Hermitian manifold means that you have a certain metric on the complex tangent bundle. And you also give yourself E to be a holomorphic, again, Hermitian vector bundle equipped with a Hermitian metric. Then what we do is that we consider the Dolbeault complex of smooth sections of the anti-holomorphic exterior algebra, tensors with E, equipped with the Dolbeault operator. And so this complex has finite dimensional cohomology, which I call H of X and E. So let me introduce something from linear algebra, and we'll come back to this later. To make things very precise, I introduce lambda to be the determinant of this cohomology. Okay, if you don't know what the determinant is, I will come back to this later. In this case, you can think of determinant of being highest exterior power. That's a complex line. And since there are cohomologies in various degrees, you have to tensor these determinants by taking into account the degree. But let me not be too specific. So lambda is a complex line. And so what Quillen metrics theory tells you is that the two given metrics, GTX and GE, determine a canonical so-called Quillen metric, lambda, double bar lambda, on this line, on this complex line lambda. And this metric is constructed via the so-called zeta function regularized determinant of the Hodge Laplacian. I will explain later on what this zeta function regularized determinant. Of course, a Laplacian doesn't have a classical determinant, so you find a zeta function way of constructing ultimately the determinant. And so what I'm saying is that this metric is obtained from the matrix GTX and GE via this zeta function regularized determinant. Now, the point about the theory of the Quillen matrix is that this matrix has a number of extraordinary properties. So I will describe some of them. So let me give the purpose of the course now. So to put this in line, let me remind you the Riemann-Roch-Hirzebruch formula, which is a formula for the Euler characteristic of a given vector bundle on a complex manifold. And we will view this Quillen matrix as being, in some sense, refined Euler characteristic. The introduction of a metric will enrich the Riemann-Roch-Hirzebruch theorem, or for that matter, the Grothendieck-Riemann-Roch theorem, to a theory of refined Euler characteristics. We will explain one fundamental formula of Quillen matrix, which is the so-called curvature theorem for Quillen matrix. When you have a line bundle varying like this in families, when you have such a family of manifold X, lambda becomes a complex line bundle with metric. So I will explain in particular one of very important results, that the curvature theorem for the Quillen matrix. I will also explain some of the functorial properties of this matrix. How do these metrics behave under natural functorial maps? And also immediately state, before getting into the course, applications of Quillen matrix. So one motivating application in particular for the development of higher dimensional Quillen matrix was number theory and Arakelov geometry, which is a form of number theory, arithmetic number theory, which deals in particular with metrics. Applications to moduli spaces, to mathematical physics, mirror symmetry, Gromov-Witten invariance, BCOV torsion, and so on. I will only briefly describe some of these applications. But let me just point out that the reason why Quillen metrics are important in the theory of moduli space is that precisely when you have a moduli space construction, generally there is a natural Quillen metric which is associated from the metric with the metric data. In particular, in the case of Calabi-Yau manifolds, so ultimately analytic so-called Raysinger torsion or analytic torsion turns out to define an important invariant over the moduli space that you consider. So first of all, linear algebra. Okay, so part of the course I will first of all develop the theory in the context of finite dimensional vector spaces, which means that I will replace the Dolbeault complex just by a finite dimensional vector space or by a finite dimensional complex. By doing this in a finite dimensional context, I will eliminate all the analytic difficulties, but also I will do more, because ultimately this finite dimensional theory will be also important, ultimately, in establishing functorial properties of the Quillen matrix itself. But for the moment, just take it as a baby example. So I introduce L to be the category of complex lines. I do not want to talk about the set of complex lines, because it does not make sense. So I talk L to be the category of complex lines, and I introduce K to be the category of finite dimensional complex vector spaces. So you have a certain determinant functor, which to a vector space associates its determinant. The determinant of a vector space is its highest exterior power, lambda max of E. So this determinant functor is multiplicative in the sense that the determinant of a direct sum is just a tensor product of the determinants. Let me point out here that there are already problems of signs, because if you interchange E and F, the order is interchanged. So effectively, if I was rigorous completely, I should have to take into account these signs. I will ignore completely the sign question here because we'll deal with metrics, and metrics don't see the signs in the different isomorphisms. So let me also point out that in this context, for the sake of consistency, you have to decide that the determinant of the zero vector space is not 0, it is just C. In this case, C is just the complex line, the complex canonical line. Okay, so what is the difference between C and any line? It's because C has a canonical section which is 1.
Wait, I don't think I understand what you mean by signs here.
Sorry?
What do you mean by the sign?
Well, because if you interchange E and F, det of E lambda max at the level of lambda max, you see that there is a -1 to the sign of the product of dimension, which comes in. And so the determinant, you will not have det of E plus F is isomorphic. I mean, you have to introduce some sign.
That's it.
Okay, so in the theory, you have to take into account the sign question, which I will ignore here completely.
Okay.
Also, let me point out that in the whole course, in this whole theory, when we talk about a vector space, a complex line, it is up to canonical isomorphism. What does mean up to canonical isomorphism? So what this means is that, for instance, if I take a complex vector space and C, it is not a priori the same thing as C. To obtain C, you need to fix a non-zero section. So ultimately, any complex line with a canonical non-zero section will be identified with C. Okay, Hermitian vector spaces and their determinant. Now we'll replace the category of complex vector spaces by Hermitian vector spaces equipped with a Hermitian metric. And so we have L bar, the category of Hermitian complex lines, and K bar, the category of Hermitian complex spaces. And again, we have a determinant functor. If you have a Hermitian vector space, its highest exterior power inherits a canonical Hermitian metric.
Morphisms are just arbitrary linear maps?
Sorry?
Morphisms are arbitrary linear maps or bounded linear maps?
So if you see that,
what are morphisms?
Yes. So,
what are they?
You know, a priori you should take isometries to preserve the metric.
Isometries, okay.
Yes.
Okay.
I mean,
Okay.
Automorphism of this theory are isometries, yes?
Okay. So
Yes.
you're just considering isomorphisms?
Yes.
Okay.
Okay, now we're going to see how does this metric behave under exact sequences. Okay, so I'll now take an exact sequence of vector spaces. Okay, so you have v squared equals 0, this you know, and we assume that there is no cohomology, that H, the cohomology groups, vanish. We will assume this for the moment. Then I define the determinant of E. That's a tensor product of determinant lines. So it's the det of EI, the highest exterior power, to -1 to the I. So what means this -1 to the I? In the theory of complex lines, it's natural to say, first of all, you have the tensor product operation, lambda tensor mu, in the category L, and it's natural to say that lambda star is canonically isomorphic to C. If you think of it, this is the canonical isomorphism is just the identity map of lambda. And so it's natural to say that lambda star is just lambda -1. That's the definition. Okay, so in the context here, determinant of E is just an alternate target, the determinant of the I, either you take it or you take its dual. Okay, I'm claiming in this context that there is a canonical non-zero section of this determinant of E. This is because the complex is exact. So let me just explain what the construction is. I just take for the moment the case m equals 1. So you take sigma 0 to be in lambda max of E0 and sigma 0 non-zero. And you take its image, V of sigma 0, which is in lambda max of E1. And it is non-zero. And so this tau of V is just a product of sigma 0, not with V of sigma 0, but with its inverse, its dual. Okay? There is a natural notion of a section and a dual section. And it's very easy to see that this thing does not depend on the choice of sigma 0. So more generally, you can iterate the construction when m is arbitrary by just pick sigma 0, v sigma 0, extend to sigma 1, etc. That's very easy. So in this case, the determinant line has a canonical section, which I call tau of v. Now, let me see how does this behave when you choose pickup metrics. I introduce a Hermitian metric, which is a direct sum of metrics of the various EIs. And I call double bar det of E the induced metric on the determinant line. So it's natural in this context to say, how do I compute the norm of the canonical section? What is the formula for the norm of the canonical section? Since it's a positive number, I write it as exponential of TE. And it turns out that TE will be, in some sense, a baby example of what analytic torsion is for the complex EV. So let me give the formula for this norm of tau of V squared. So you introduce the associated Hodge Laplacian, V anti-commuted with V star, which is invertible because the sequence is exact. And so here is the formula for this exponential of TE. That's a very easy formula that you can compute for yourself. It's an alternate product of classical determinants of the Hodge Laplacian in various degrees, in all the possible degrees. So this is the Hodge Laplacian restricted to EI, but there is a certain power, which is -1 to the I. This more or less is familiar, but there is this extra I. Okay, this is the so-called analytic torsion in a finite dimensional context, and this gives you the formula for the norm of the canonical section.
Sorry, can you explain the notation T to the E?
Sorry?
What is T to the E?
Excuse me?
What is T to the E?
Oh, that's a tautological definition. You just define T to the E to be the log of the norm of tau of V squared. Okay. When eventually in the course, E will be replaced by Dolbeau complex. So E will be eventually become infinite dimensional. And actually, we'll have to find a zeta function regularized version of the determinant to get the Quillen metric. But for the moment, it's just, it's just tautologically defined by the formula.
So sorry, is T to the E defined only up to a multiple of 2 pi I, or
Excuse me?
is T to the E defined up to a multiple of 2
No.
pi I?
No.
It's a real number.
No. It's D to the E is real.
It's a real number.
Okay, it's a real number. Okay, we'll how in the
Okay.
real is metrics, so it's a real number. So let me just point out that if you delete the I here, you just get 1. That's very, very easy statement. That's again a consequence of the fact that the sequence is exact. So, in some sense, what this second line detects is that in this case, the Euler characteristic, that is the alternate sum of the dimensions of E, is 0. But analytic torsion gives you already a refined invariant. And this refined invariant is obtained via this I, hence the name derived Euler characteristic. Introducing the power I gives the origin derived.
So if you shift the complex, does that add 1 to the...
Sorry?
If you shift the complex homologically, does that add 1 or something to the...
I mean, shifting doesn't do anything.
It won't change it?
No, it won't change it.
Oh,
Basically, it doesn't change it because of what I said, because the formula below, we say to you that shift is irrelevant.
Yeah, I see.
Yeah.
The x is going to be multiplied by 1.
Yeah.
I see, okay.
Okay, now let's go to the case where E is non-exact. So, I assume now that E is non-exact. So, H will be the cohomology of EV. So, I claim that there is a canonical isomorphism, that of E canonically identified with that of H. Okay, let's try to understand this canonical isomorphism in the case where there is the sequence is exact. That is in the case where H vanishes. So when H vanishes, this side here is determinant of 0, and this is C. I told you determinant of 0 is C. And so this isomorphism means that that of E has a canonical non-zero section. That's section tau of V. Okay, this is exactly the meaning of this canonical isomorphism. And again, the canonical isomorphism can be easily obtained by constructing a sequence of exact sequences to which you apply the isomorphism that their determinant is canonically equal to C. Okay, I won't do that. This is a very easy statement. To get the canonical isomorphism, that's just an extension of the construction of the section 2 of V I gave before. Now, let me call H script to be the so-called harmonic objects, that is, which lie in the kernel of the corresponding Hodge Laplacian of the Hodge. Yeah, I was going to say Hodge Laplacian VV star, harmonic object. So by finite dimensional Hodge theory, we know that H, the cohomology, is canonically isomorphic to the harmonic objects. Now, the harmonic objects are a subspace of the complex EV, so they inherit a metric. From the metric of E, you get a metric on the harmonic objects. From the metric on the harmonic objects, you get a metric on the cohomology. And so, you get a corresponding metric on the determinant of the cohomology. This is just obtained via so-called Hodge theory. Now we have two objects, each of them has a metric, that of E and that of H. And the question is to know what is the relation between the two metrics, since they are two lines are canonically isomorphic. So let me define again TE as before as an alternate product of determinants, but where I simply exclude the zero eigenvalue. Okay, in these determinants I exclude the zero eigenvalue to avoid, I exclude in some sense the harmonic object. I exclude the cohomology. And so the formula here just tells you that once you identify that of H and that of E, the relation is a sort of obvious one. It's a product of squared that of H times again this exponential of TE. This formula reduces to the previous one in the exact case. in the exact case, this should be viewed as just a norm. Det of H is just C. That means that you have to replace on the left-hand side the section 1 by 2 of V, and you recover the formula I gave before. In the context of Quillen metrics, what here is a tautological statement will eventually become a definition. In the context where E itself becomes infinite dimensional, will eventually be the Dolbeault complex. This identity, which is here a triviality in some sense, will become a definition.
What do you mean by excluding the zero eigenvalue?
Sorry?
What do you mean by excluding?
Well, because if you take the determinant of a non-invertible operator, you get 0.
Right.
So you exclude the zero eigenvalue, take the product of eigenvalues, non-zero.
You take the orthogonal complement of the zero
Yes,
eigenspace?
yeah,
Oh, okay.
yeah,
Okay.
yeah.
Okay.
Yeah, understood.
Okay.
I mean, that's a way of proving this by just splitting, just use the splitting and then apply the theory before. Okay, now let me go to the case of holomorphic complexes, where the situation I considered before is not with vector spaces, but with vector bundles. So again, X is a compact complex manifold, or complex manifold for the moment, doesn't matter. So I give myself EV exactly a holomorphic complex. That is, I assume that the EI's are holomorphic vector bundles, and that the V's depend holomorphically on the base parameter. So that's a holomorphic complex of vector bundles, and GE is a Hermitian metric on E. So in this case, the det of E becomes a holomorphic line bundle. The holomorphic structure comes from the structure of the EI's, and the metric double bar det of E is just a metric inherited from the metric of E as before. So, in general, H, which is the pointwise cohomology of this complex, in general, it is not a vector bundle. It can jump. Okay, so the typical example, that a causal complex, you take here that a complex over C, Z is a coordinate on C, and you take E0 to be C, E1 to be C, and the map V is just multiplication by Z. You see well that this H vanishes except at Z equals 0. So in general, H is not a vector bundle. Actually, the best way to think of H is to think of it as a coherent sheaf. I won't go here in this connection with coherent sheaves. I will mention some things about coherent sheaves later. So H is not a vector bundle, but I'm claiming that there is a fiber-wise canonical isomorphism between that of E and that of H, that the isomorphism that we mentioned before. And which means that even though the det of H itself is not well defined as a vector bundle because H jumps, but still it has a sort of canonical holomorphic extension. Okay, and that's that of E. So that of H is not a good line bundle, but that of E is. Okay, in the context of coherent sheaves, this will say that the coherent sheaf still has a nice determinant. Okay, that's the Knudsen-Mumford theory. I won't go into this, but that's important to realize that that of E is always well defined, even though that of H is not well defined. In the context where E itself will be a Dolbeault complex, the det of the cohomology, again, is not a vector bundle. And the det of omega, the det of the Dolbeault complex, is not well defined, because omega, the Dolbeault complex, is infinite dimension. In some sense, the theory of Quillen metrics will just erase this difficulty, take the best on the side of Dolbeault complex, the best on the side of harmonic, of finite dimensional cohomology, and makes it all of this still make sense.
When you say, do you mean like for the Dolbeault complex for a family of complex manifolds over a base? Is that what you're thinking of?
Yes, exactly. The family of Dolbeault complexes is a smooth family.
Yeah.
Okay, it's very good,
Yeah.
but it's infinite dimension.
Sure.
So the theory, I mean, in some sense, the theory of direct images is done to overcome this sort of difficulty, and in the context of Quillen metrics, will overcome these two. So let me point out that the previous identity I gave is still valid pointwise. It's certainly not an identity of metrics in general on a line bundle, except, of course, in the case where H itself turns out to be constant dimensional, where it is a vector bundle, and then this identity becomes an identity on isomorphic, holomorphic line bundles. Okay, so in some sense, one decides, if I just was proceeding naively, I would say that of H does not exist, but I replace that of H by that of E, and I decide that that of H coincide is just the Hermitian line bundle that of E equipped with its canonical metric. In some sense, when you have the Dolbeault complex, again, this is exactly what we will do. We will obtain the Quillen metric by exactly a similar sort of construction, but with the identity here, which was before tautological, becomes now a definition.
I'm a little confused. Doesn't that formula suggest that you should use the metric?
Sorry?
Doesn't that the formula on the second to last line suggest that you should use the metric on determinant of E rescaled by x of t to the e?
If you want, sorry? If you scale the metric?
Doesn't that I don't understand the jump between the second to last line and the last line. The second to last line suggests that you should
Because
rescale.
this identity is still true pointwise. You just fix a point.
But that,
I think he's saying that there's a correction corresponding to the exponential.
So,
You know that you about dealing with the that
no,
H.
when ultimately, in the theory, in the proper theory, the det of H will be defined to be that of E. That will be ultimately its definition.
okay.
Okay, that's exactly what you do. When you have coherent sheaf, you find a resolution, and you say the det of the coherent sheaf is just the det of the resolution.
Right, but the metric, doesn't that suggest that the metric, to be quasi-isomorphism invariant, doesn't that suggest that the metric should be rescaled?
The metric is here depends on the choice of metric on E. It's not canonically associated with H, right? I mean, the metric comes from the metric on E. Okay, so that's the same thing with Quillen metrics, right? I mean, you're not happy with the metric coming from harmonic forms. You just correct it by something which comes from the whole determinant of the Laplacian. It is from a global thing on the manifold. That's exactly the point. Okay? Okay, so let me go again to the section 2 of V. So in the case where EV is exact, is pointwise exact, the section 2 of V becomes a holomorphic section. Remember, I had told you that the determinant of a complex, of an exact complex of vector spaces as a canonical section. I'm saying that this canonical section is now holomorphic in the parameter. It's just holomorphic by its construction. Look at the formula and you see well that it's holomorphic. So, in this case, when you have a line bubble with a non-zero section, you have a relation between the norm of the canonical section and the curvature of the line bundle. So this identity here, minus d bar d log, etc., is equal to the C1 of that of E, equipped with its canonical metric. That's a sort of tautology. That's the curvature equation. Once I will apply this curvature equation in the context of Dolbeault complexes, that is, when I will eventually replace the vector bundle E finite dimension by the infinite dimensional Dolbeault complexes, this identity, which is sort of trivial, will become the curvature formula for Quillen metrics. Okay, so let me just rewrite this. I just wrote the log of tau of v squared to be the exponential of TE. And now you look at this identity here. This identity, which is sort of trivial, if you just think of it just abstractly, you see that it's not, I mean, if you try to prove it directly from the formulas I gave you by this alternate sum of determinants, and obtain directly this formula from this curvature equation from the formula, you see that it's non-trivial. So I will now explain what will be the algebraic mechanism which will allow us to prove such formulas, and then eventually in the course explain how it can be properly extended to infinite dimensions.
I think there's a question.
Yes?
Should you take an integral on the left here? Some kind of
Sorry?
should you take some kind of an integral on the left side?
No. No, there is no integral here. Log of tau of v squared is just TE. TE, yes, that's the definition. Tau of v squared was exponential. Okay? So you see that this identity is non-trivial. I mean, of course it's trivial by the way we obtained it. But as an identity on determinants, it's non-trivial. Okay, so we'll develop the formalism which will allow us to prove this and eventually apply it in infinite dimensions.
The right-hand side is defined to be the curvature form for the line.
Yes, the C1 of a line bundle, you know that you use a chain connection on the line bundle. Okay, so of course, if H turns out, if the cohomology turns out to be a holomorphic vector bundle, that is, if the cohomology groups have constant dimensions, you can refine the previous identity to say that the d bar d of TE is equal to the difference of the C1s of the two metrics. Okay. We will view such an identity eventually as a transgression equation. Okay. So maybe you know Chern-Simons theory, which allows you to write canonically the difference of two characteristic forms as a d of something. There is a corresponding theory that I will shortly explain in the context of complex circular bundles, which is Bode-Chern theory, in which you replace the de Rham operator by the d bar d operator. Okay, so eventually the construction of TE will fall in that category of saying we have ultimately two line bundles equipped with two distinct metrics. How can I write canonically the difference of the C1 as being the d bar d of something?
So I'm very confused about this last. Can you go back one slide, please?
Yes.
What's the relation between these last two formulas? It seems like is the last one only valid when H is holomorphic vector bundle?
Yes, it only makes sense if H is holomorphic vector bundle. Okay.
Otherwise, it seems like it's. How does it consistent with the recursion above?
This is the case where there is no cohomology. That is, that of H is trivial.
Ah.
Okay, that's the previous case, a case where the thing was exact.
Ah, okay, I see.
Okay, now if it's not exact, but there is still a holomorphic vector bundle, okay, so we will now introduce Quillen's superconnections. So it turns out that Quillen has had two absolutely fundamental but independent ideas. The idea of the Quillen metric, which is developed in an article, 3 pages article, and the idea of superconnections. And unfortunately, I was never able, when talking to him, to know whether for him there was some connection or superconnection between the two. Okay. But what we will show is that actually we will eventually derive the theory of Quillen metrics from Quillen's theory of superconnections. Okay, so I go back to the previous context. In the previous context, so E again is a holomorphic complex of vector bundles. So, Hermitian, again, it's Hermitian here. There is also Hermitian metric. So let me introduce nabla E to be the Chern connection. So we have the nabla E second, which comes from the holomorphic structure, and the nabla E prime, which is just, in some sense, a dual of nabla E second, which gives you the corresponding unitary connection. Okay, now let me briefly explain what this object is. This is a differential, this A second, which is obtained by putting together the two differentials V plus nabla E second.
We have a question. Is T to the E smooth even when the homology of the complex is not a vector bundle?
Sorry, is what is?
So when the homology is not a vector of the bundle, T to the E is a function on the base.
T as E is a function.
Is it-
it's
is-
of course a non-smooth one.
Oh, okay, that's
So
what I was
it's very irregular. I mean,
Okay.
you know, it can typically be like log of Z squared. Log of Z squared is well defined except at Z equals 0.
Okay.
Okay? So in that case, the curvature equation becomes of its direct mass at 0, which is an extra direct mass. But let's forget about this. So you look at this V plus nabla E second. Okay, and you view this V and nabla E second as odd, so that naturally, because of holomorphy, they anti-commute. Okay, so A second is a Quillen superconnection. I mean, I would say that I won't give you the abstract definition of what a superconnection is, but you can think of it as a NOD operator, which verifies the proper Leibniz property with respect to multiplication by forms. Okay, that's an extended D-bar operator, if you like. And because of holomorphy, A second square is equal to 0. Okay, so we have exactly the same as QA squared before. We have this A second square is equal to 0. That's anti-holomorphic superconnection. It only contains actually differentiation in the 0-1 direction. Now, in this context, we can define. Okay, so let me slightly modify. Yes?
How was nabla E broken into prime and double prime parts?
Oh, nabla E second, when you have a holomorphic vector bundle, nabla E second is just a differential which defines the vector bundle as being a holomorphic one. Okay, that's what's given to you. Okay, you know that there is the Nuremberg theorem which tells you that giving yourself a holomorphic vector bundle or having a holomorphic differential which square vanishes is the same thing.
So it's just a 0-1 part?
Yes, it's 0. No. I mean, you have the 0 part, and then the metric determines the 1-0 part. That's a Chern connection. The 0 part is canonical. It only depends on the vector part. The 1-0 part depends on the 0 part and on the metric. The combination of the two defines a Chern connection. Okay?
I'm just asking the notation, double prime, is it the same as the 0-1 part?
Yes, double prime, yes. The second, yes. That's the 0-1 part, yes, absolutely. Yeah. So, I will just make one parameter family of metrics on our vector bundle E.
What is V?
Sorry?
Little v?
So little v is a differential.
Oh.
You have the complex EV. Okay, so you put together, in some sense, the pointwise vertical differential and horizontal differential nabla second. Put the two together. Then, I will now define a one-parameter metric family of metrics, which consists in scaling the metric in different degree. But the scaling depends on the degree. So it scales like t to the n, where n is a number operator of the complex. I mean, n acts on E likes I. On EI acts on EI by multiplication by I. That's a number operator. Okay, so I scale the matrix, change the scaling. That's a natural change of scale. And then I define the adjoint of the A-second with respect to this new matrix. Okay, so you know what, if the base was just a point, if there was just little map V, you would take the adjoint and you would find that the adjoint of V with respect to the scale metric is just T V star. V star is just the adjoint for the given metric. That means that you just scale the adjoint by T. This is what happens when there is no base, when the base is a point. If there was no V, you would say the adjoint of nabla S second is nabla E prime. Sorry, I should have interchanged the two, but it doesn't matter. Okay, and then you combine the two adjoints. There is a natural way, there is a natural theory of duality in which actually you can view this A prime T as being the natural adjoint of A second with respect to the metric GET. And then you have this very easy identity which describes a variation of this A prime T with respect to T. So, what are we going to do with this? Exactly as when I had the Chern connection, I have now the Chern superconnection, if you like, Quillen superconnection by summing A second and its adjoint, A second plus A prime T. Then what Quillen taught us was that we could use superconnections exactly as we use connections in Chern-Weil theory. Okay, when you have Chern-Weil theory, you give yourself a connection, take its curvature, which is the square of the connection, and take the trace of exponential of the curvature. Here you do exactly the same thing, but Quillen's theory. You take the curvature of the superconnection, which is a tensor again. That's very easy to verify. And you take its supertrace. Okay, so supertrace alternates sum of traces on the ERs. So you get the differential form of the base. It's very easy to see that this form is also a sum of forms of type PP. Okay, it's known that the curvature, when you have a holomorphic vector bundle, is sums of forms of type PP because curvature is of type 1, 1. That's exactly the same thing here. Exactly the same thing here. Let me, before moving to the next slide, that this notion of anti-holomorphic superconnection, actually, when you take its more general form, that is any object but with many more terms, instead of having two terms like nabla S second plus V, you can consider more general objects with terms in every degree. And then it turns out that this new theory describes actually all possible coherent sheaves. Okay, that's, in some sense, this is a description of holomorphic complexes. On any complex manifold, coherent sheaves are described in terms of this longer.
So it's phi?
Sorry?
So it's phi?
Excuse me?
Phi.
Oh, phi is just a 2i pi normalization.
Okay.
Okay, so you get the Chern character form. Now, let me give a transgression formula. Okay, so I introduce again this previous form, the alpha t, which is a supertrace of exponential minus a squared t, then the Chern character form. And then I just slightly modify this form by introducing a number operator. Large M, trace, but there is this extra large M. Remember, there is this minus 1 to the I times I. We try to justify the introduction of the I.
Wait, sorry. At the content of on the last line of the last slide, that was the left-hand side. Are you saying that? I'm not quite sure. What is the definition of that left-hand side? If not,
Okay, I mean that's the definition of Chern character form associated. There should be the extra a second. Okay, coming, I take into account the circumflexion. So in other words,
So that last line is a definition, basically.
that's a definition, yes.
Okay.
Yes, the definition. In this context, it's the definition.
And the theorem is that actually, if X has topology, those are actually
Yes,
the
yes,
Chern
the
classes.
theorem of Quillen tells you that it lives in the same cohomology class
Yeah,
as the original Chern character.
okay.
But actually, what we will follow now is a D bar D cohomology class. Okay, so, okay? Yes, so maybe you are at the end?
Yeah, at the end.
Okay, so let me just take the final formula. It tells you that the variation of alpha t of these Chern character forms, it is not a D of something like a Chern-Simons theorem. It is a D bar D of something. Okay. And it's a D bar D of gamma t over t. Okay, maybe I will stop here. Okay, now at this point what we have done is develop a theory in a finite dimensional context. There is still no proper Quillen metrics. But we have in some sense the abstract language which then, when we will consider family of double complexes, we will try to use the same sort of algebraic formalism. It will not completely work, but almost. Okay, thank you very much.
I think we have time for one question. Okay, if not, then let's thank our speaker again, and then go outside for the group
We
picture.
have a group photo just outside the hotel, the main entrance.
Thanks.